Now, a fun fact is that a curve C does not have a unique representation by a vector function. For example, if we have r1 of t equals t squared, t cubed, and t is between 1 and 2, we could also say this is going to be the same when r2 of u is equal to e to the u, e to the 2u, e to the 3u, where u is between 0 and natural log of 2. If you graphed both of these vector-valued functions, they'd be the exact same thing. So we have different parameterizations. R and R2 are called parameterizations of C, hence why I just said they're different parameterizations. So suppose we have this C is given by R of t, and t is between a and b, R is continuous, and R of t traverses C exactly once. We can define the arc length function, S of t, to be a to t, the integral, of the magnitude of r prime of u du. What's really nice about this reparameterization of r? Well, what you're going to see is this is the arc length formula. Now, with the arc length formula, that tells us the distance, right? So every moment that we move in t is just going to be a unit. So when we have this arc length parameterization of a function, then we aren't going to have to go through the messiness of calculating the arc length every single time. We can just use our arc length parameterization. We'll talk about this a little bit more. Now, suppose we could solve this equation for t in terms of s. In other words, we invert s of t so that way t equaled s of t. Now, we are going to reparameterize r of t, with r being r of t of s, where s is between 0 and the length. Length is the arc length, t was a to b originally. Let's do an example of this so it makes sense. Reparameterize r of t, which is t, 3 cosine of t, 3 sine of t, between -5 and 5 with respect to the arc length. This is the same function that we dealt with before. So if you recall in your notes, what I had done is that the magnitude of r prime of t was just going to be the square root of 10. So if we have s of t being the integral from a to t of this, so square root of 10 du, it is just a is -5, our starting point. We have square root of 10 t plus 5 square root of 10. Now we want to find the inverse here. And how do we do that? We switch our points. This is s. And this is square root of 10t plus 5 square root of t. And we just solve for t. So we get s minus 5 square root of t, square root of 10 all over the square root of 10 equals t. This is our t of s. So how do we reparameterize r of t? Well, at this point, we just plug our values of t into r of t. So our arc length reparameterization is just going to be r of t of s, which we just plug in this for t. So we have s minus 5 root 10 over root 10, then 3 cosine of s minus 5 root 10 over root 10. And since I'm running out of room, comma, this is bad notation, but 3 sine of s minus 5 root 10 over root 10. And that is going to be our arc length parameterization. And S would be between 0 and this 10 square root of 10. So remember what I said was that it moves in arc length, kind of. It moves in length. So S ends at the length of R. Because we remember we found that this was the length of our parameterization here. So if I moved 5 S units, I would have gone 5 units along the curve. That's what's really nice about this arc length reparameterization. To be more explicit with what I was talking about is let's look at dr over ds with our arc length of reparameterization, which was d over ds of r of t of s, which we can use our rules of derivatives to say that this is dt ds times r prime of t of s, which is equal to 1 over the magnitude of r prime of t times r prime of t of s. So the magnitude of the dr ds is equal to 1. So that means the arc length reparameterizes always moves with unit speed, right? The slope, in other words, with respect to s is always 1. We just move at units of 1 consistently.